So good morning, everybody, and thank you for being here today. My name is Damien Furfaro. I'm a PhD student of Professor Richard Saurel. The research work I'm going to present deals with a simple HLLC-type Riemann solver for compressible, hyperbolic, non-equilibrium two-phase flows. The method I'm going to present is easy to code and very robust. Its accuracy is validated against exact solutions as well as experimental data. Well, the compressible two-phase flows computation involves some difficulties. The first difficulty is to take into account the mixture cells. Indeed, in the cells filled with a pure fluid, the Riemann solver equations, the Euler equations, are valid. Here, for example, with a pure gas, or here with a pure liquid. But subtle work has to be done in the cases of mixture cells. The second difficulty is to find a good model and its appropriate resolution method to treat all these cases. That is, drops, slugs, and bubbles. But the model on which is based our resolution method is able to treat all these configurations. The starting point of the analysis is the Saurel symmetric variant of the Barre-Nunziato model, which was proposed in 2003. It corresponds to a hyperbolic system of partial differential equations with 7 equations, each phase having its own set of mass, momentum, and energy balance equation. The seventh equation expresses the volume fraction transport with the transport velocity ui and involves a pressure relaxation term. Each phase evolves with its own density, velocity, and pressure, and its own subvolume. The system is symmetric in the sense that indexes of the phases can be reversed without changing the results. What are the properties of this model? The interfacial variables are symmetric. We can see here the interfacial velocity, ui, and interfacial pressure. The volume average pressure and interface velocities are given by these expressions. Moreover, the mechanical equilibrium state is reached at the end of relaxation processes controlled by the following rates, which are respectively the pressure and velocity relaxation rates. Finally, the system is closed thanks thermodynamically. Z is the acoustic impedance, density multiplied by the sound velocity. The system is closed thermodynamically thanks to the relation between the internal energy of the phase and the pressure and the density of the phase. The system fulfills the second law of thermodynamics. But there are some issues to derive a resolution method. The first difficulty is the numerical approximation of non-conservative terms when the functions are discontinuous. If we take the case of this term, interfacial pressure, which is multiplied by the gradient of volume fraction, we have to deal with products of Heaviside and Dirac functions. Heaviside is for the interfacial pressure, which is discontinuous across the shock wave. And the Dirac function is a gradient of the volume fraction across the interface. When the shock wave interacts with an interface, there is a problem. The second difficulty is the presence of 7 not-order waves, rendering the resolution of the Riemann problem difficult. Former contributions for the building of numerical schemes. In 1999, Saurel and Abgrall built the first good enough type scheme, but it was too diffusive. In 2003, Andrianov, Saurel, and Varnek continued to work on this approach. Abgrall and Saurel in 2003 made the Discrete Equation Method, which was a very efficient method, but computationally expensive. Schwendemann, Val, and Capilla worked on this subject, but they needed for regularization and had some issues in the presence of Choc interface interactions. Deladic and Pape Alexandrix built an exact solver with same issues. Tokareva and Toro in 2010 made an use the HLLC solver with 6 waves, but with same issues. Recently, Ambroso, Chalon, and Raviard in 2012 considered 7 waves with an algorithm free of regularization method. Our present work reuses the Discrete Equation Method, which was developed by Abgrall and Saurel in 2003. This method consists in integrating Riemann problem solution of the Euler equation on a given two-phase topology. Here is presented the stratified flow reference topology used in the DIM. If we consider a given cell boundary here, we can see that 4 types of contact are possible. The contact 1, 1, 2, 2, 1, 2, and 2, 1. For each flow channel is solved independently of the others and has a constant height during the hyperbolic step. It means that volume fraction are locally frozen. It also means that interface motion and wave dynamics are assumed 1D, multi-D effects being considered in relaxation terms, omitted during the Riemann problem resolution. So the Riemann problem solutions are average in each subvolume and provide a set of discrete equations. The continuous limit of this numerical scheme, when both space and time steps tend to 0, provides a set of PDEs being a symmetric variant of Barrel and Nunziato model. This method is both accurate and robust. However, this method is not so easy to implement and computationally expensive. These arguments motivate our present work, in which a simpler method, easier to code, and even more robust, is presented. It's time to rewrite the two-phase flow model previously presented. The Saurel and Hall symmetric variant of Barrel and Nunziato model can be written as follows. We can see non-conservative terms here, which is function of interfacial pressure and interfacial velocities. Here is the conservative variable vector, and here the flux, which also is a function of interfacial variables. Let's now concentrate on the determination of these interfacial variables. At each cell boundary, the determination of the interfacial variables UI and PI is based on the 2D topology with decoupled flow channels previously presented. The The interfacial variable's determinations depends on the type of contact between the two phases, contact 1-2 or contact 2-1. The lower script L and R are relative respectively to the left and right states. For each contact, the Riemann problem of the Euler equation with two different fluids has to be solved. Contact 2-1 appears when alpha 1L is smaller than alpha 1R. Here we can see the corresponding XT diagram in the HLLC solver frame. W represents the set of variables of the Euler equations. The left and right facing wave speeds are estimated with the Davis approximation, which is written like this. The interfacial velocity is estimated under the HLL approximation. HLLC is used to calculate the interfacial pressure. The contact 1-2 is a symmetric situation when alpha 1L is taller than alpha 1R. The corresponding XT diagram in the HLLC solver frame is here, and the estimations are made with the Davis approximation for the left and right facing, as previously, and HLL is used for interfacial velocity, and HLLC is used for the interfacial pressure. As the Riemann problem solution for contacts 1-2 and 2-1 depends only on initial states left and right, variables ui and pi are locally constant during a time step at a given cell boundary, and this is an important point. As these variables are local constants at a given cell boundary, the initial PDE's system can be expressed locally in conservative form. So the non-conservative term volume fraction multiplied by the gradient of hk, which depends only on ui and pi, vanishes. Locally, we only consider the conservative form of the equation with the conservative variable vector and the flux. This remark significantly simplifies the two-phase Riemann problem resolution. It's time to present our two-phase Riemann problem solver, Riemann solver. The Riemann problem for a given phase is decoupled from the Riemann problem of the other phase, as ui and pi are local constants. Here we can see a schematic representation of the Riemann problem for a given phase k in the HLLC frame. We propose a 4 waves Riemann solver for each phase. The 4 waves are SLK and SRK, which are the left and right facing wave speeds. The intermediate contact wave speeds, SMK, and the interfacial velocity. WK denotes the vector of primitive variables of a given phase with volume fraction, density, velocity, and pressure as components. The states WLK and WRK are respectively the initial left and right states. The Rankine-Hugger relations across the various waves link the initial data to the intermediate states. SL and SRK are estimated with the Davis approximation, and the contact wave is calculated thanks to the HLL approximation. We can see here the presence of non-conservative term, which depend on interfacial pressure. So, for each phase, we have to solve the Riemann problem with these 4 waves. two wave configurations are considered for a phase, for a given phase. Case A, when SMK is smaller than UI, and case 2, when UI is smaller than SMK. In the following, only the configuration A will be considered. Across each wave, the Rankine-Gounod of the local conservative system is written as follows. For example, the Rankine-Gounod relations across the wave SL link the WAK state to the WLK star state. Same thing for the other relations. To compute the flux in each intermediate state, the conservative variable vectors are needed. Across the contact wave, particularly across the contact wave SMK, we obtain the expected follows. Indeed, pressure and velocity are constant across the intermediate contact waves. Moreover, as the interfacial velocity is a local constant, the volume fraction equation expresses in a local conservative form. So Rankine-Gounod relations can be easily applied to obtain these equations. The Rankine-Gounod jumps are in perfect agreement with the non-conservative formulation of the volume fraction equation. The main difficulty relies in the determination of the velocity URK star, which is here in this state. To do this, mass and momentum jump relations across the various waves are considered, but a complex expression for URK star is thus obtained. After tedious calculation, we obtain the unexpected result, URK star, which is equal to the contact wave speed. Consequently, all intermediate velocities are equal. This unexpected result can be explained if we consider the calculation of SMK. SMK was calculated with the HLL approximation, but its calculation takes into account the contact with the other phase through non-conservative terms. So we obtain this result, which simplifies all the calculations. In the following, we haven't written the other Riemann problem solution variables for the sake of simplicity. The three intermediate states conservative variable vectors are thus easily obtained. We obtained the conservative variable vectors for each state, intermediate. The fluxes in the various intermediate states are deduced from that. And with the help of the intermediate states and fluxes, the last step consists in the solution sampling. An important property of this solver is the solver's agreement with the second law of thermodynamics. Bouchu results in 2004 showed that enables to show the entropy production across the wave speeds SLK and SRK, the positive entropy production. But what about the entropy production across the wave UI, separating states WK double star and WK star? With the help of the energy jump relation across this wave and the Gibbs identity, the entropy jump is written as follows. we have to prove the positivity of this term. If we specify the calculation to phase 1, 2 instances have to be considered. We find again the contact 2,1 and the contact 1,2, depending on the sign of the volume fraction difference. For each contact, we can easily prove the positivity of this term. So the entropy prediction across wave UI is also positive. There is no difficulty to make the same proof with the phase 2, for the phase 2. Well, having the two-phase Riemann solver in hand, we are able to derive a good enough type scheme. As the entire cell is now considered, it is not possible to consider local conservative formulation. This system is thus considered under the form which is written here, with the non-conservative term, depending on the interfacial velocity and pressures. For a given cell, the good enough scheme reads like that. Here is only the first order version of the good enough type, the good enough scheme, for the sake of simplicity. This formulation agrees with the non-conservative treatment of this term of the discrete equation method. Well, our resolution method is validated against exact solution as well as experimental data. In all tests that follow, the materials are assumed governed by the Stephen gas equation of state. That summarizes agitation and attractive effects in a simple formulation between the internal energy, the density, and the pressure of the phase, with 2 parameters, gamma and P infini. Stiff mechanical relaxation effects may be used to solve interfacial flows in order to fulfill interface condition or of equal pressures and equal normal velocities. In the following, velocity non-equilibrium two-phase flow are addressed first. At the second time, the method capabilities to deal with single velocity flows with the help of stiff relaxation solver will be addressed. All tests are achieved with CFL, which is equal to 0.8. Okay, let's consider the first test, which is a velocity disequilibrium two-phase flow test. Here, consider a shock tube filled with a liquid water and gas. The volume fraction is uniform everywhere. The left chamber has a high pressure of 1000 MPa, and the right chamber has atmospheric pressure. In this context, no source nor relaxation terms are used in this run. The numerical results are in symbols and are compared to the exact solutions with lines. As the volume fraction is uniform and relaxation effects absent, the wave UI, interfacial velocity, has no influence in the Riemann problem solution. So, if we consider the pressure, we can see that the water curve, we can see the water curve with dark symbols, and the gas pressure with gray symbols. And we can show a perfect agreement with the exact solution. Second test. Here we consider a discontinuous volume fraction. On the left, in the left chamber, we consider only a nearly pure liquid. And on the right chamber, we consider a gas, a nearly pure gas. The left chamber has a high pressure of 200 MPa, and the right chamber has a as an atmospheric pressure. No source, no relaxation term are used in this run. In absence of the relaxation terms, each fluid evolves with its own pressure and velocity. Dark symbols are for water, and gray symbols are for gas. There is no interaction between fluids. This test puts in evidence the contribution of the non-conservative terms. In the left chamber, the liquid is nearly pure and is expanded by a strong rarefaction wave. The solution of the rarefaction wave is in perfect agreement with the exact one obtained with a pure liquid on the left and pure gas on the right. In the left chamber, the gas is expanded too. It accelerates near the interface because its volume varies in space and time. In the right chamber, a shock wave propagates in the gas. Gas variables are in good agreement with the exact solution in the right chamber. The liquid is also accelerated by the shock wave in its negligible volume. But the most important point is that interfacial conditions are perfectly matched. Here we can see the interfacial condition for pressure and for velocity. So these results show that the numerical method is able to deal with multiphase mixture in non-equilibrium velocity, as well as interface problem separating pure or nearly pure materials. Interface conditions are matched as a consequence of non-conservative terms and do not need relaxation ones, which are absent in this context. Let's now consider a double expansion of a two-phase mixture. We consider again liquid water and gas with a volume fraction uniform everywhere. Here, stiff pressure relaxation is activated, is used everywhere. The numerical results are compared to not exact solution. The numerical results are compared to with the DIM solution, the Discrete Equation Method. So if we consider the gas volume fraction, we can see an increase at the tube center as a consequence of pressure relaxation terms. The relative velocity increase is also, appears too as a consequence of compressibility differences among the fluids. But the results show a good agreement with the DIM results. Phase separation by sedimentation. A 1 meter height vertical tube is considered, filled with liquid water and air. The tube is closed at both ends. At the initial state, the two-phase mixture is subjective to gravity acceleration. So the heavy fluid falls down and the light one goes up. At equilibrium state, the lower half tube is filled with water and the upper half tube is filled with air. So the method is able to separate the phases. Let's now consider the ROG test problem, which was made in 1998. A vertical shock tube is considered, filled with nearly pure gas, Particles bed is settled on a grid and set to motion when an incident shock wave interacts with it. So, a transmitted shock wave propagates in the particles bed, and a reflected shock wave is emitted. During particle motion, gas and particles have intense relative motion. Two pressure gauges are used to record the pressure history at two locations: before and after the particles bed. Solid particles are considered compressible and governed by the Stephen-Gage equation of state. Here, the numerical results are with the dark symbols, and the rogue pressure signals are with gray symbols. We can show a good agreement. The particle layer? Yeah. And we use a drag force. As a source term. The next test is the velocity equilibrium two-phase flow test. Here we consider an interface separating two fluids. In the left chamber we have nearly pure liquid, and on the right chamber we have a nearly pure gas. The high pressure is in the left chamber with 200 MPa. Stiff velocity and pressure relaxation solvers are used. This is an important point. So, interfacial conditions are perfectly matched thanks to relaxation effects. Finally, the last test consider a shock tube with two mixtures. Here we consider aluminum and liquid water. The volume fractions are uniform everywhere. The left chamber is with an high pressure, and the right chamber with an atmospheric pressure. Stiff velocity and pressure relaxation solver are used too. In this context, volume fraction vary in both compression and expansion waves. The limit model that is solved with the present method corresponds to the mechanical equilibrium model of Capella 2001, because we consider one pressure and one velocity, thanks to stiff velocity and pressure relaxation terms. The numerical results are compared with the exact solution of the Capella model, and we can show an excellent agreement. Conclusions. A new method has been built to solve non-equilibrium two-phase flows. This method is simpler than existing good enough type schemes in this area, and is of comparable accuracy and robustness as the discrete equation method. When dealing with a larger number of fluids, the new method is expected to be more and more efficient as it chooses a single HLLC resolution per phase, while the discrete equation method uses n-squared Riemann problem resolutions, where n represents the number of fluids. Thanks for your attention.
Can you please show slide number 9 again? I think, I'm not sure of the number, but it's with your equations. Yeah, the one just before 8. Okay. Just.
We have the 7 equation models, which is rewritten here. For a given phase k, we have the mass, momentum, and energy balance equations, and the volume fraction.
Can you please highlight the difference with the Bauer-Nunziato model? It's the H term, is it?
The variant,
Have you written?
the variant approach of Saurel and Al of the Bauer-Nunziato model is the interfacial variables, which are symmetric. Here, UI and PI are expressed with these relations.
Okay.
So this model is symmetric, thanks to that.
Do you know maybe if the model is hyperbolic in meaning?
The model is hyperbolic,
okay,
with 7 waves, with 7 velocities.
Okay.
That are the velocities used in our Riemann solver presented here. You have UI, which is one of the velocities, eigenvalues. I thought the term. We have U minus C, U plus C, some phase, and SM, which is U, for each phase. So 7 ways, 7 eigenvalues.
Another question?
Yes, sure.
I have another question. Have you tested out your resolution method on other cases than Riemann problems?
I didn't.
Have you tested it on other cases than just Riemann problems, like
Chalk tube?
Like yes, for instance. Yeah. Yeah. Okay.
Well, mainly. I worked on chalk tubes, all these test cases that I have presented.
Okay. Okay.
Other question? Yes. No.
All right, thank you for the presentation. Yeah, I wanted to come back on this because I didn't get everything. So basically you get UI and PI by solving the sub-Riemann problem at the interface, following if
for a given is
alpha is smaller on the left or on the right. And then, so you do HLC solver for each phase k. So SMK is the interfacial velocity of the pure phase k.
No, it's not the interfacial velocity, it's the contact.
Contact discontinuity, yes. Sorry.
No problem.
And
interfacial velocity between two different fruits.
Yes, but then you come to the conclusion that the velocities are equal in all the intermediate states.
Yeah, it was an unexpected result.
And for both phases.
The velocity of the phase in each intermediate state for a given phase are equal.
Yeah, but the velocity of SMK is u, and the velocity of the contact is also u. So all those waves have the same velocity, haven't they?
We have calculated at the first step UI. UI, interfacial variable, is known. After we use this solver approach, and with the help of the Rankine-Hugoniot relations, we obtain that all velocities are equal across the wave SM, K, and UI.
So
all velocity
U star K is equal to UI?
Yeah, all the velocities at the intermediate states are equal to SMK.
Oh, to SMK. So, okay.
Yes, here.
Oh, but it's different to UI.
Yeah.
Okay, so the interfacial velocity is moving within. Okay.
UI enables the... But SMK takes into account too the interaction with the other phase.
No, but it makes sense because you get SMK from HLLC, so you're
From HLL.
From HLL, so your states in the middle are mean states.
Yeah.
Okay. I have another question.
Okay.
It's about your relaxation parameter mu, and the relaxation solvers.
Okay.
So what do you mean by relaxation solver?
Okay. If we consider the initial model of Saurel, we remark the source terms, which are relaxation terms, with differences of pressure and velocity. We remark the time terms. So we consider only after the good enough step, we consider a new system. Only a system which is made with the time terms and the source terms. We don't consider the fluxes and the non-conservative terms present here.
Okay, so you split your operators and you keep only the source terms without mu.
Yes,
we
keep the source terms, and we tend the parameters mu and lambda to the infinity.
Okay. Good.
And we have a resolution method, very particular.
Okay, can I have a last question? It's on. It may be test case on slide 21. I'm not very sure.
Okay.
But yes, on the bottom left, why don't you reach equilibrium pressure on the far right? You should.
Can you repeat, please? I didn't understand.
Why don't so on the far left you have 200 megapascals, and you have equilibrium of pressure in the liquid part. And then on the far right, you have a pressure difference when you should have at the beginning you had equilibrium of pressures in your initial state at 1 atmosphere.
Yeah, at the initial state.
Is it gone far away or?
At the initial state, the left chamber had a pressure validated for both fluids, but the liquid is nearly pure in the left chamber. On the right chamber, the same thing, but with atmospheric pressure, and this is a gas which is nearly pure. That are initial states.
Yes, but the pressure of the liquid is also equal to the pressure of the gas in this part.
At T is equal to 0, okay. But when the run goes, we can observe that in a given part of the choke tube, left or right, pressures are different between fluids, and pressure and velocities again.
Yes, but you must have somewhere far right where both liquid and gas pressure are equals to the atmospheric pressure.
At the interfacial conditions.
Oh, so you like cut
here?
No, when your pressure goes up to 100 atmospheres or 100 megapascals. The liquid, the dark cross.
Yeah.
And you must have somewhere where you have equilibrium of pressures. So the pressure of the liquid is equal to the pressure of the gas, no?
Pressure of the liquid is equal to the pressure of the gas only at 0.8 at the interface, at the material interface. Thanks to non-conservative terms only, because relaxation terms are absent here. This test just puts in evidence the contribution of the non-conservative terms.
Okay, let's talk about that later.
Okay.
Thank you.
Sorry if I didn't...